about geometric meaning of toroidal compactifications of moduli.
Thank you very much. It's a pleasure to be here. Thank you for the invitation. The last time I was here, this building was under construction, and now it's all finished and very nice. It's still very cold outside. Here's what I would like to talk about. And principally, I will talk about the moduli space AG. And so this is the moduli space of principally polarized abelian varieties. And it has infinitely many toroidal compactifications. And these compactifications correspond to fans, so fans tau. And just as in ordinary toric geometry, there are infinitely many fans, so there are infinitely many compactifications of a torus. Here, there are infinitely many fans, and there are infinitely many of these toroidal compactifications. And so, what is the tau here? I kept this part from the pre-talk, so let me just review what's written on this blackboard. So we start with some.
Which one should we look at?
This one. It doesn't hurt. You'll learn something about abelian varieties, how they are very similar to toric varieties. But this part. So you start with some sigma, which is a z to the g, just free abelian group. And then you...
That's a lambda.
Lambda. And you look at a symmetric square of lambda. Thank you. You can write in, using matrices, you can think of it as half integral matrices. So integers on the main diagonal, half integers of diagonal. And then you look at the dual group. And the dual group will not look like this. Instead, the dual group will be integral symmetric matrices. So now symmetric, but integers everywhere. And these two lattices play exactly the same role as the usual standard lattices M and N in toric geometry. So the N lattice is responsible for fans, and the M lattice is responsible for polytopes, or infinite polyhedra. And the fan tau has to satisfy now the following three properties. So this is a fan on NR, on the real vector space corresponding to N. And the support of this fan has to be C plus bar. So let me describe what this is. That part I erased. So you start with the cone C plus. And this is the cone of all positive definite real quadratic forms. It's an open cone. And then you look at its rational closure. So C plus bar is generated over real non-negative, with real non-negative coefficients by Q's, which are semi-positive definite and rational. So you add something on the boundary, but only the rational matrices. So in particular, you add countably many arrays. And then count. So far, nothing inside. So your rational closure is an infinite polyhedral cone now. And this fan has to have support, see this rational closure. So now it will look, so you start with this infinite polyhedral cone and you divide it into infinitely many manageable pieces. So every piece now is finitely generated instead of being infinitely generated. That's a fan. And secondly, it has to be invariant under GLGZ. GLGZ acts naturally on lambda that we started with, and therefore it acts on everything else, acts on matrices. Under this action, these cones have to go to themselves. And mod GLGZ, there has to be only finitely many cones. So that's the kinds of fans you consider.
I assume that the vertices are rational.
Right, so rational fan. Mm-hmm.
Can we call it?
So all the generators are rational. And so for every such fan, you have a compactification, toroidal compactification of AG. And what I'd like to discuss is the geometric meaning of these toroidal compactifications. Now, let me briefly mention that there is a theory due to Katsuya Kato and other people that understand these compactifications as some kind of moduli spaces of log abelian varieties, or as some moduli spaces of SL2 orbits, or nilpotent orbits, or degenerations of pure Hodge structures.
Why do you have condition 3 there? Why do you need there here?
So, for example, divisors, the boundary divisors on this compactification, they will correspond to one-dimensional cones, but modular GLGZ. And so if I have infinitely many such orbits, then I'm in trouble. So I should have only finitely many boundary divisors and only finitely many boundary strata. So where was I? So there is one interpretation of these toroidal compactifications as spaces parametrizing, say, degenerations of Hodge structures that are compatible with tau. So whose monodromy, you look at degenerations, whose monodromy is compatible with tau. And so as you can see, this tau appears in the question, and then it appears in the answer. And so what instead I would like to, I would like to discuss questions where tau does not appear in the question, but somehow, one of these tau appears in the answer. Right. So tau somehow should come. We don't specify it in advance, so to say. And so it's known that there is one. This is an old story, so let me recall some old story. The so-called second Voronoi fan. The toroidal compactification for this second Voronoi fan has a natural geometric interpretation, has a natural geometric meaning. So any point, if you look at the k-bar at the geometric point of this toroidal compactification, then it corresponds to a pair, or you can say a triple like this, where X is a projective variety and tau is an ample Cartier divisor, and G is a group variety. It's a semi-abelian group variety. So it's either a torus or an abelian variety or something in between, something mixed. So an example of such a triple would be a rational nodal curve with a point, and that's a projective variety. That's your Cartier divisor, ample Cartier divisor, and you have C star acting on it. So just just go from there. So moreover, if you look at the pair X, epsilon, tau, then it's stable in the sense of minimal model program. And so what I mean by that is it's like a stable curve, only a stable higher dimensional variety. And so this, what I mean by this is the canonical class of this pair is ample. And moreover, canonical kx is just 0. And I added something ample. And the pair has semi-log canonical singularities. So you should think stable curves here. So that's what this is the analog of. So there is already this compactification, one of them. And so you can ask this moduli question intrinsically. You can start with such pairs, define such stable pairs, and then ask what the moduli space is. And this moduli space, modulo some finite details, it corresponds to this second Voronoi toroidal compactification. Moreover, the usual Torelli map, so the Torelli map, you start with a curve, C curve, a genus G curve, and you look at its Jacobian. That's a principally polarized abelian variety. So this map can be extended to compactifications. And this extension has a geometric meaning. Mainly, now you start with a stable curve, and you send it to Jacobian, but you want an abelian variety with a theta divisor. So really this, you want a projective variety with a theta divisor. So this variety really corresponds to compactified Jacobian in degree G minus 1, and peak zero acts on it. So in this modular interpretation, you don't compactify families of abelian varieties, but families of torsors. So torsors with divisors. Okay? So that's an old story. What I want to ask in this talk is whether other compactifications have a similar geometric meaning. Okay. This one we know, but what about the others? And so for that, the two sub-questions are, what other toroidal compactifications out there? What are some interesting ones that one can look at? And secondly, why suspect a geometric meaning for them? And let me start with answering the first question. So answer 1. There are at least 2 more classical toroidal compactifications. Now, I should say that so there are the perfect cones, and otherwise called the first Voronoi fan. And then there is central cones, and the compactification, the corresponding toroidal compactification for this one is the blow up of the Satake compactification along the boundary. So AG bar is the Satake minimal compactification.
When you say blow up, you guys go from the bottom up several blocks.
So you just take the look at the boundary with reduced scheme structure and just blow it up. This is known as Igusa blow up. Igusa looked at this blow up in dimensions in G up to 4, and he proved that in those cases you actually get a resolution of singularities of Satake, compactification. In higher dimensions, if you do just this, then it's some non-normal variety, so you need to normalize. So normalize. And then it's a toroidal compactification, and you can describe the fan, and I'll tell you in a second what this fan is. Cent for central cones. So there are these two toroidal compactifications. And the second one, you can already appreciate that this is, it has some geometric meaning, not as a moduli, but looking at the space itself. And historically, that was the first toroidal compactification to be constructed. It's a very natural thing to look at. Now, let me say a few words about the perfect cones. First of all, let me define these two compactifications, and then I will tell you several very nice properties of this perfect compactification. So here's the definition. As I said, you have two lattices, M and N, and this M was the symmetric square of lambda, and N was the dual to that. These are half-integral lattices. These are half-integral symmetric matrices. These are integral symmetric matrices. And in both spaces, you have this cone C+. And in the space N, I will even look at its closure. So in the M space, you can look at, you can take the C+ and intersect with, consider all the non-zero integral points inside. There will be countably many of them. You look at the convex hull, and what you get is an infinite polyhedron with countably many faces. So take the convex hull of that, and this convex hull is called a core. This is a canonical core associated with this picture. And that, take the normal fan to that. So normal fan will live in the N space. That normal fan is the central cones. That's the definition. So the polyhedral is in M. The normal fan means that for every facet you look at a normal vector. Normal vector will be in the dual space. And so the normal fan will be in the N lattice. So you get some fan. That's the definition of the central cones. Uh-huh. Okay. All right. Thank you. I'll try. And the perfect cones are described almost the same, but just looking at this picture. So what you do is you look at the integral points in this cone. There will be countably many on the boundary. And in fact, all the generators will be on the boundary. So that's the theorem. And you take the convex hull of that. So we'll draw the convex hull. And take those as generators. So take the convex hull and take the cone over it. So similar picture, but in this space. This is the definition of the perfect fan. That's called a perfect compactification. Uh-huh.
So where's the subdivision?
Right. So look at all the integral points except 0. Yeah, take the convex hull of that. The convex hull, again, will be a polyhedron, infinite polyhedron, kind of going up, going inside. Look at the faces of this convex hull and just cone over it. So here I would take this convex hull and then look at the faces of it, and these faces would give me the cones. Was that clear? Let me try again. So these are, let's say these are the integral points. I look at the convex non-zero integral points. Right, but the convex hull, there will be some points inside. But I look at the boundary. So the boundary has countably many faces, and just take cones over them. So these are your cones. Therefore, the rays, the one-dimensional generators, they correspond to integral points on the boundary. Of this convex hull, of this infinite polyhedral figure.
Still the infinite polyhedron, not just the big cone.
Right. So you get there are countably many such integral points on the boundary, so there will be countably many rays. And let me say right away that it's a theorem of Barnes and Kohn that these generators, they just correspond to squares of linear forms. They are quadratic non-negative forms that are very simple, just squares of some integral quadratic forms. Okay. So that defines the perfect compactification. Yes. So the first Voronoi fan and second Voronoi fan were defined by Voronoi in the beginning of the 19th century, and without any regard to algebraic geometry. It's just it's a way to split all the positive definite quadratic forms into some manageable classes and some manageable cones. So that was the question. Can you divide all quadratic forms into finitely many classes in a nice way? And Igusa defined his fan, by just looking at this blow up, and then from that you can figure out what the combinatorics is. There is the second Voronoi compactification. Let me say it very briefly. So the second Voronoi compactification, there is a rational map to the perfect compactification. It's regular for G up to 5, and really rational for G starting with 6. And it's slightly mysterious what's going on. And this is part of the question. Does the perfect compactification have a moduli meaning? And secondly, does this map have a moduli meaning? So both of these questions are interesting. But let me say a few nice things about the perfect compactification, and then I will try to answer my question too. Why do I suspect that it has some moduli interpretation? But for the orientation, could the organizers tell me exactly what time I started?
11:25.
1125. All right. So here are the nice things about the perfect compactification. The Picard group of AG perfect has rank 2. And this is the smallest it could be. There is one generator corresponding to the interior, to AG itself, so some Hodge class. And then there is only one boundary divisor, so only one boundary divisor. And here's how you can see it. So the boundary divisors correspond to one-dimensional cones in this fan, modular GLGZ. And as I told you by theorem of Barnes and Cohn, these rays, these generators on the boundary, they are just squares of linear integral forms. And you can send any integral linear form to another integral linear form primitive by GLGZ. Therefore, modular GLGZ, there is just one class. And so there is only one boundary divisor. For all the other compactifications, there are lots of other points inside. So this is from the point of view of minimal model program. If you care about curves and divisors and Mori cone and birational geometry, then this is very good news. This is the most optimistic it could be. That's one. Secondly, the canonical class of AG perfect, is ample relative to the Satake compactification. So if you look relatively, this AG perfect, as any toroidal compactification, it maps to Satake. And you can just, so that compactification has Picard number 1. You can look relatively, and then relatively, this canonical class is ample. And I put script AG because in this statement, it's a stack. But let's ignore that subtle difference. And the stack, again, AG perfect, has terminal singularities. Oh, yeah, terminal singularities. And the coarse moduli space will have singularities which are finite quotients of these. So finite quotients of terminal singularities. So how do you see these two properties easily? You can see them just from the definition. And with enough experience with toric geometry, just by looking at this picture, it should be obvious, both of these properties. So what this definition should remind you, it should remind you the definition of a toric Fano variety. So for a toric Fano variety, you start in the lattice N. You start with some fan such that the closest integral points on the rays form a convex polytope. And in that case, minus k is ample. And the variety X has canonical singularities if there are some points somewhere integral points in the middle. And it has terminal singularities if all the integral points are outside.
No points inside that.
Right. No points inside means canonical. And if there are also no points on the boundary like this, then it's terminal. So this picture is exactly the same, only inverted the other way. I'm taking a convex hull of all the integral points. So if you look at the rays, this picture is convex, but the opposite way. And there are no points, no other integral points on the boundary. by definition. And so therefore, it's like anti-Fano. So the canonical class is ample, and it has terminal singularities. The difference is that this statement was for a toric variety itself, and the analog of it here is it's relative over Satake. So you think of Satake as like a minimal object in this category, a point to which everything maps. So the fan describes what happens relatively. Now the nice properties continue, and a much stronger statement was proved by Shepard-Baron, who proved that the canonical, that first of all for, I think, G starting with 6, the coarse moduli space itself has canonical singularities. Not just finite quotients of canonical singularities, but actually canonical singularities. And for G starting with 11, the canonical class is an F. Not just relatively, but absolutely. And this is what we call a minimal model in birational geometry. So it's a minimal model of any resolution of singularities of it. And for G starting with 12, the canonical class is actually ample. So it's also the canonical model. Okay. So this is the nicest, really, the nicest compactification from the point of view of birational geometry. And this fan itself was computed for G up to 9. It is really the easiest. These fans are pretty complicated, these periodic fans. And this one is the easiest. And 9 is a high number by the standards here. For the second Voronoi compactification was only computed up to genus 5, and the central as well. It's very, they become really complicated in higher genus. So the perfect compactification was computed up to genus 6 just by hands, without any computer. All the cones. Yep. Mm-hmm. Mostly the maximal cones. So the minimal cones are trivial. They're just squares of linear forms. But then the maximal cones, how many types are there? And for example, in genus 6, there are 7 types, etc.
Computed by who?
In low genus, classically in the 19th century by Korkins, Alterov, and then Voronoi. In genus 6, this is a result of Barnes. About 30 years ago, maybe 40 years ago, and just by hand, so he computes seven maximal dimensional cones. And then higher dimension, that's done by computers, by people like Valentin and, I may misquote, but there are German people, combinatorics people in Germany who wrote some computer programs. Say again? Right, types of modular GLGZ, right. Mm-hmm. Okay, so, all right, so now maybe I can get to the second question. So why suspect any moduli meaning? And the motivation is from curves. So moduli of curves is mg bar alpha. So there are these spaces mg bar alpha, which were defined by Hassett and Kiel and other people as the log canonical models of mg bar, of the Deligne-Mumford compactification with respect to the boundary, but then weighted by some coefficient. And this coefficient is some number less or equal than 1. And briefly, the geography of these modular spaces is as follows. So this is the line for alpha, and I'll start at 1, and I will go down somewhere to 0, or I'll move in the direction of 0. So if you start just put 1 for alpha, then you get mg bar. And then up to 7 over 9 over 11, it does not change. And then at 9 over 11, there is a contraction. And this moduli space has an interpretation itself. So it's a moduli. This is a moduli of curves with cusps, but no elliptic tails. So elliptic tails are not allowed, but cusps are allowed. And then up to 7 over 10, again, there are no changes. And then there is another contraction for 7 over 10. And this is a flipping contraction. So there is in the minimal model, if you do the minimal model program, you have to make a flip. And then you can continue. But moreover, this space has a modular meaning. And the next space has a conjectural modular meaning. So there is a chain of these modular spaces that have conjecturally, at least, some of them not conjecturally in the beginning, but conjecturally, there is this infinite chain of modular spaces that are, first of all, they are log canonical models, so they are significant from this MMP point of view. But secondly, they are modular of something. And then the question is this. You know, there is MG, and then there is AG bar, and there is a Torelli map going this way. So the question is, can you also put a chain of spaces on the bottom for abelian varieties so that they change maybe I'll put some beta 1 and beta 2 and beta 3. Is there a chain of compactifications of AG or something similar? And steps in the minimal model program, so this line will be MMP, similar to that. And each of them has a modular interpretation, and at least this map, all these vertical maps, this Torelli map, so instead of one extended Torelli map, you have infinitely many extended Torelli map, and they're all somehow geometrically significant. So they describe, you start with a curve like this, and you probably send it to its compactified Jacobian.
So you start with the second Voronoi.
Aha, and so then the question is, you know, what should you start with, right? And as you maybe observed here, I hope I convinced you that from the point of view of birational geometry, it's the perfect compactification that's nice. So if you expect something here, some chain here, then it's the perfect compactification you should begin with. And then there is already these steps. There is already a very natural answer what these steps should be. So the rank of Picard group for the perfect compactification is two-dimensional. And therefore, the Mori cone of curves lives in a two-dimensional space. The space of curves modular numerical equivalence, numerical equivalence is two-dimensional, and the cone looks like this. And one of the rays corresponds to a map to to the Satake compactification. And then there is the second extremal ray. And so therefore, you can look at the external contraction corresponding to the second ray. And after, it will be a flip. And after you've done this flip, there will be, again, a two-dimensional cone. And you have a second array, and you can look at a flip for that. And you can continue. And this is known as the two-ray game. So the very standard thing in minimal model program. Every time you start with a two-dimensional cone, you can do this. Play a two-ray game. Uh-huh.
But AG is the other end. Is the low canonical model of Satake.
Right. So the perfect compactification, it was the canonical model itself. So this B1 would be 0 somehow. Not 1, but 0. And those numbers will be, in some sense, negative. So that's the motivation. So that's the indication that perhaps the perfect compactification has some geometric meaning.
Did you put a level structure on like the whole board, like this?
For what? For which purpose?
MGs and for today the MGs to the.
No, I don't. We're getting in those tricky questions. You know, what kind of level structure you have to put on a stable curve, etc. Abelian, non-abelian. But I'm doing it without level structure. So I'm either working with stacks or with coarse modular spaces. So this is true for either one. Right. So let's not worry about level structures. Okay. So to test this hypothesis, the first step is this step. So we know that the Torelli map extends to the second Voronoi compactification. But this picture suggests that maybe it should extend to the perfect compactification. And here, let me tell you a little history of the question. The question of whether mg bar, whether the usual Torelli map extends to a map to a toroidal compactification was first discussed by Namikawa in 1973. And he looked at the Igusa blow-up. So in these terms, he looked at the central cone compactification. And the question is, is that regular? is the extended rational map, is it actually regular? So what he could do is that he proved that it's regular for genus up to 6, although maybe genus 6 is stated, not proved, but so it's regular for low G, and it's a conjecture, so he formulated it as a conjecture for all G. He couldn't prove it. He set out to prove it, but couldn't quite prove it. So got into some combinatorial difficulties. So that's the whole story started in 1973, and then in 1976 or so, Mumford came up with a very easy combinatorial argument showing that the map to the second Voronoi compactification is regular. And really, then people started thinking, that it should have a moduli meaning then, that they should have a geometric meaning. And so this is written up in a paper of Nabikava where he investigated the second Voronoi compactification. And the question for the perfect compactification, as far as I know, nobody investigated it before. So that's. But now we have a motivation to ask that question. I posed many questions already. Let me start giving some answers. And so let me answer the 2 question marks here. And that also gives me a chance to highlight what smart students I have. And so the first 2 theorems are from a joint paper with Adrian Brunyate, who's a student of mine. And here are the theorems. So the first theorem is that you look at mg bar and you have this rational map to the Igusa blow-up. And you pick a point of mg bar. A point corresponds to a curve, stable curve, maybe like this, right? And then for the stable curve, you have the dual graph. And the dual graph of this curve is like this. You have a dual graph. And then this T is regular in a neighborhood of this curve C, if and only if on the first cohomology of this graph there exists a simply laced root system such that the vectors corresponding to the edges are roots. So in the cohomology for every edge, there is a vector which I denote EI star. So just look at the definition of cohomology. It's the cochains. That's free abelian group on the edges, modula co-boundaries. And so there is a finite abelian group. For each edge in your graph, there's a vector. Say again? Right, finitely generated. Thank you. Finitely generated abelian group. So Z to the G, where G is the genus of the graph, in this case 2. There are finitely many vectors, and that's a combinatorial interpretation or description. If there is a root system for which these are some of the roots, then it's regular. If there isn't, then there isn't.
But, I mean, This sounds like finite monotony.
Okay, well, maybe you can tell me afterwards what maybe you have an easier solution. What it tells you. But so these root systems, simply laced root systems are just AN and DN and EN. DN for n starting with 4 and EN for 6, 7, 8. And direct sums of this. Right? These are also root systems. And moreover, if gamma is without loops and Q connected, then this root system has to be irreducible. So it's only one copy, either AN or DN or E6, E7, E8. And so now all you have to know is what kind of curves correspond to AN, and what are the AN curves, and what are the DN curves, and what are the EN curves. And the answers are as follows. So this AN type, so there exists a root system of type AN if and only if the graph is planar. So that there exists an embedding of this graph into S2. And there exists a DN if and only if the graph is projective planar. It can be embedded into RP2. And there exists an EN, and I have no idea. So I don't know what the answer is. And I asked the best experts in the world on graph theory this question. So you have planar graphs and projective planar graphs. What are the analogous? Are there analogous classical classes sort of graphs in genus 6, 7, 8? And nobody knows, but maybe you know. But that's a very legitimate question. But the corollary to that is that for genus up to 5, this map mg bar to ag to the Igusa blow-up is regular. That's just because up to genus 5, every graph is either planar or projective planar. And for genus 9 and higher, it is not regular. And that's because you just pick a graph without loops to connect it, which is not projectively planar. Not planar and not projective planar. Such graphs exist. And that's it. You have a counterexample. And so note that EN only appears for 6, 7, 8. So if the genus is 9 and higher, then you're OK. Oh yeah, I can make you a graph. Let's see. You start with this, and then this graph. So, for example, this graph. So that's genus 9. Without those 3 last things that had type E6, and now it's genus 9. Another question?
Couldn't you have E6 plus A3? I mean, that you said that for genus bigger than or equal to 9. Doesn't appear.
Yeah. That's even but then it's not irreducible. Then it's just a direct sum. So that's not a counterexample. So I want something irreducible, and so I really cannot just add them together. OK, and well, there is still a question of 6, 7, 8, and here we looked at this with Livingston and Joe Tenini, another student of mine who is here, and a few more co-authors. Patrick McFadden is here, and Maxim Arab. And so we concluded that T is regular for for G equals 6, 7, 8 as well. And so here you have to look at all the graphs in genus 6, 7, 8, which are not projectively planar. There are only finitely many of them, so it's a finite computation. Really easy for genus 6, a little harder in genus 7. Massive computation for G equals 8, but it's a computation. So that's the complete answer for that. Now for the perfect compactification, that's the one I was really interested in.
You say a gamma has H1 is z to the G. So you're only looking at like particular stable curves. I mean, it could be smaller.
The G's are different.
So as I said, in genus up to 5, is that small?
I'm just saying, if you have a stable curve, the dual graph doesn't necessarily have any H1 at all.
Yeah. So for every genus, you look at that genus and all the smaller ones. So the statement is, start with a smooth curve. This group is trivial, so there is a trivial root system, and therefore it's regular.
No, I think he's worried that the G is the same as the G for mg, or is it the same? Because you have mg bar, but then you have h1 gamma z equals z to the g. Are those
It's sufficient to look at the most degenerate in each genus.
So for the regularity, you have to look at the G as in mg and every G before that. Okay. So a little confusion, but hopefully that's very clear. Okay, so the perfect compactification, and that's a theorem with Brunyate again. And the statement is that for any G, the map to the perfect compactification is regular if and only if on the first cohomology there exists a quadratic form, Q, such that the length of these vectors, of the standard vectors, are 1. And for any other non-zero vector, the length is at least 1. So there is a metric for which these are among the shortest vectors, If there is a root system, then just the root vectors have square 2, just divide by 2 to make an agreement with the statement, because the quadratic form there is even. And this is always true for any G. So therefore, the map to the perfect compactification is always regular. And the proof is, in the proof, there are pictures like this. And for anyone who looked into theory of nodes and skein relations, this looks very similar, but not the same. And again, I would be very interested to know if anybody has seen pictures like this before. So these are like knot diagrams, but these are graphs, not knots. All right. Well, my time is, ticking down. Let me very briefly discuss the modular interpretation of the perfect compactification. So here's what I can prove. I can prove that any point in a perfect compactification. To to any such point, I can associate in a unique way a polarized projective variety X without the divisor, just with an ample line bundle. But this variety is the compactification of that semi-abelian group. I can do the torsors too, but this is more interesting. So for an abelian variety, that will be an abelian variety itself, not a torsor over it. But L is not a principal polarization, but a multiple. So for every point, I have a geometric object, projective variety associated to it. And now the question is, can you fit these objects into a family? And here, unfortunately, I can prove a little less. So for the canonical Q factorialization, over the canonical Q factorialization, I can construct a family of such varieties. And if you take 2 points here that map to the same point in the perfect compactification, then the varieties are the same. So a toric variety is Q factorial if and only if all the cones are simplicial. And if the fan is not simplicial, then there is a unique canonical way to make it simplicial, to subdivide to a simplicial fan. And similarly for these toroidal compactifications. And so over that, I can construct this. And let me draw a couple of pictures, and I'll stop at this. I'll just tell you what the geometric meaning, what is that geometric object? So I'll start with a perfect cone. Third part before that. There exists an open part in the second Voronoi compactification and in a perfect compactification, which contains the image of mg bar. So these are really distinct. I told you that there is a rational map like this, which for high genus is not regular. But they share a common open neighborhood of the image. And over this neighborhood, so over the image of mg, for the second Voronoi, the family is the family of compactified Picars in degree g minus 1. But this family that I'm describing here, this family is the compactifications of peak 0 and not peak g minus 1. So the geometric meaning is different. So the second Voronoi compactifies the torsors over abelian varieties. And what I'm suggesting that this perfect compactification, the meaning should be that it compactifies abelian varieties themselves, the limits of abelian varieties themselves. And
in those cases, you're taking the semi-stability condition with respect to the canonical polarization of the curve?
Yes, right. So in genus g minus 1, it doesn't matter. But in in degree 0, yes. So if you take a look at a perfect cone, then as I told you, the rays correspond to linear forms. And for these linear forms, you can look at a picture like this. You can look at a system of hyperplanes where these linear forms are integers. And so this pictures like this describe the family of these compactified Jacobians in degree g minus 1. And if you add to every integer, if you add a 1/2, then pictures like that describe the compactified Jacobians of peak 0 combinatorially. But for any perfect cone, you have a collection of these linear forms, so you can look at the corresponding pictures. And this can be interpreted as a projective variety. That should be perfectly obvious to everybody, right? So every polytope is a toric variety. And so you have lots of toric varieties glued together. And then you divide this by z squared. And you have only finitely many toric varieties glued together. And so you get a projective variety. So a point in the perfect compactification comes with a picture like this. So there is a natural projective variety associated to it. And it just comes from this picture. And I'll stop.
When you say that L is a multiple of the principal polarization, is it a fixed multiple?
For every G, it's a fixed multiple. I'll tell you where it appears, where it comes from. So if these linear forms intersect nicely, and nicely mean the intersection points are integral, then principal polarization works. But in general, they intersect badly, so that some of these are fractional. And then you need a multiple to make them integral. And that's the multiple. Yes, please.
So if you want if you want to map from the moduli space of cusps, and you want to send things to the compactified Jacobians, you're going to have some fibers which are not semi-abelian varieties. Do you know any do you know any space with any modular meaning in which such things appear?
Yes.
Can you say which one it is?
Right. So it's the first flip of this AG perfect. And that's additional motivation for all this moduli picture. So let me say it. So first of all, some part of AG, some interior of AG has to be contracted. And mainly the abelian varieties that can be written as a variety of dimension g minus 1 plus an elliptic curve. Such curves, the information about E is lost. And so this is where you have this curve with elliptic tail. And this elliptic tail becomes a cusp. Compactified Jacobian of such cuspidal curve is also a projective variety which has cusps. It's some compactification of you look at bg minus 1 and add an affine line and then add a cusp. So there is a natural geometric object. So you can say it should be moduli of such things. Now, for that second ray in that two-ray game, for that second ray to be contracted, Shepard-Barron proved that this always can be done in characteristic P, but not characteristic 0. And Shepard-Barron also proved that if there is a modular interpretation for the perfect compactification, and these varieties have polarization which is twice the principal polarization, then the second ray is contractible. he gave a construction for this contraction, assuming that there is a modular interpretation. So that's another hint that should exist, this modular interpretation. I never got to talk about K3 surfaces, but I'm over time. So.